Hello, and thank you all for joining us in EMWorks webinar series. So today's webinar will cover a magnetic geared permanent magnet synchronous motor used in electromobility. So we'll have a look into the simulation and analysis of a magnetic geared motor used in electromobility application. My name is Majdi, Senior Application Engineer at EMWorks, and will provide this technical presentation. So today's session is the first part of this webinar. So let's see the agenda of our webinar. So a brief introduction about magnetic geared electric machine and its main concept. Then we'll have a look into the design challenges and issues that can be posed by this machine while designing and doing the design and prototype process. After that, we'll see or demonstrate the solution that can help to overcome these issues and solve them. So which is EMWorks solution for electric machines. Two case studies will be covered during this session. The first study or case study is the simulation of a magnetic gear system. So we'll have a look into the simulation of magnetic gear. Then the second case study is the no-load analysis of a magnetic geared permanent magnet synchronous motor. So this is our second. This will be our second case study. So after that, and before ending with the QA session, we'll have a live demonstration about the solution that we are proposing. Alright, so let's start now. What is a magnetic geared permanent magnet synchronous machine? So it is this kind of machine or this kind of system is relatively new. Its concept is based on the integration of a magnetic gear. So we have a magnetic gear for power transmission is integrated inside an electric machine, whether it is an induction or a permanent magnet machine. So this combination leads to a machine with three main structures. So as a result of this combination, we got a machine with three structures. The first structure or the first component is the stator core with its winding or copper winding, as can be seen here. So as you can see here, we have the outer part or the outer component is the stator with windings. Then we have the inner rotor. This one at the center of the machine is the inner rotor, is made of a steel core with permanent magnet poles. It is low torque and high speed rotor. Then we have the third structure of this one, which is the pole, the outer rotor, which is also connected to the load, to our load. So it has a higher torque and lower speed. So there is power transmission from the inner rotor to the outer rotor, and there is amplification of the torque. So from low torque to a higher torque at the outer rotor. So this is mainly the concept of magnetic geared permanent magnet synchronous machine. So it is an integration, it is a combination of a magnetic gear for power transmission and a permanent magnet synchronous machine for a power or energy conversion from electrical energy to mechanical energy. So we have a conversion from electrical energy to mechanical energy, and this mechanical energy will be amplified through the magnetic gear, which will be used for the power transmission. So instead of two systems, we have one combined system. Let's see the advantage of this system. So the main advantages of this combination of a contactless power transmission. So we have a contactless power transmission. There is no contact in the magnetic gear. There is no contact between the inner and the outer rotor. So this power transfer or power transmission happens or achieved without any contact. So this contactless power transmission system, which is integrated inside, which is the magnetic gear, and it is integrated inside the electric motor. Precisely in our case, it's permanent magnet synchronous machine. Helps to reduce the heat and the friction losses because of the contact. If we have like a mechanical gear, we will have higher heat or higher friction losses, then we will have an important heat generated because of those losses. So here we have contactless contact-free power transmission. So there is an important reduction in the heat and the friction losses and overall the mechanical losses. And also through this contactless power transmission, we will get a better, higher or get a better power density. So we will have a better power density. So this helps to improve the efficiency of the system and the performance as well. So through these two, having a higher power density and a lower mechanical losses, we'll be able to obtain a system with improved efficiency and higher performance. This same contact-free transmission also will help to reduce the lubrifications. So there is no need for lubrification, or reduction of the lubrification, and it saves the maintenance costs. So there is a reduction on the maintenance costs. So there is because there is no contact between the inner and the outer rotor, so it helps really to reduce the maintenance costs. Okay, so issues like generated heat, vibration, noise can be also reduced or eliminated through the use of such system. So since there is no contact again between the inner and the outer rotor, so the vibration, the noise, and also the heat can be reduced. In addition to those benefits, so a protection against overload can be ensured thanks to the contactless power transmission gears. So again, thanks to this power transmission technology or system, a better protection can be provided to our system against overload damage. Okay, so finally, a very relevant point that can make such system ahead of other competitors in its domain, so is an important reduction in terms of size and weight. So here a lot of components and parts are removed because of the combination of the gear inside the magnetic gear inside the electric motor. So a lot of parts and components are removed, and this will have help to have a compact structure and reduced the size structure and weight as well. So this can make our system a great solution for electromobility applications and green energy production as well, because it can be a direct drive system, especially for wind turbine systems as well. Yeah, so these are the main advantages that can achieved through the use of a magnetic geared permanent magnet synchronous machine or magnetic geared electric machine in general. Alright, so from the previous slide we listed several design issues. EMWorks proposes a complete solution to tackle those issues, and there are many other issues that were not covered in the previous slide, so they can be also solved and overcome using the solution that we are proposing now. So this solution came with the 3 tools integrated inside the same platform. They are 3 electromagnetic simulation software. So they are integrated inside SolidWorks and Autodesk Inventor. So it's this integration is mainly to overcome issues related to easy and complex geometry creation and modification. So these tools, these CAD tools, which are SolidWorks and Autodesk Inventor, are powerful, flexible, and user-friendly. So they helps to reduce geometrical issues that can be faced. So whether your geometry is easy or complicated, so using SolidWorks and Autodesk Inventor, so you can really create and edit your geometry easily and quickly. Yeah. So moreover, Motor Wizard, which is one of the 3 tools that we are proposing in this solution. So it's a motor design and simulation software. So users can generate automatically their electric machine. So the user can automatically generate his machine through Motor Wizard based in a wide range of templates available in the software. So it came with a wide range of templates. So and the user can define based on the template or his chosen template, he can define his own variables or own parameters. So you need to define your machine properties, including geometrical parameters, machine settings, so like rated power, speed, excitation type, winding configuration. It has an automatic winding configuration, also a manual winding configuration as well for more options, and the simulation setup. So then the software will take care of the rest. So once you define those parameters, geometrical parameters, machine settings, simulation setup, the software will take care of the rest, the geometry creation, modification, and the analysis and the simulation as well. So the simulations automatically performed by the software. You just need to specify few inputs for the simulation setup, so you don't need to define everything. So just a few inputs plus the geometrical parameters, then the software will generate and create geometry based on the template that you choose. Then you run the analysis you want. So the software gives you several options for the analysis, including a quick and accurate semi-analytical solution to get plenty of results like efficiency map, power versus speed, no load analysis. Also DQ model calculation is available through the software, on load analysis, and so on. There are plenty of analysis, so you can choose whatever you want to generate the results that you need. So all of these type of analysis are available through Motor Wizard. So the second option is EMWorks 2D, which is a 2D multi-purposes 2D electromagnetic simulation software that can be used to solve any electric application, including magnetic gears and electric motors. So it's used for any application like gears, magnetic gears, electric motors, transformers, solenoids, permanent magnet application, and so on. So it helps to save time and increase the design iteration, the number of design iteration for users. So then we have EMS, which is the third tool of the solution. So of the proposed solution, it's a 3D electromagnetic simulation software. So it provides several multiphysics options like thermal, linear static, motion, and it comes with an integrated circuit simulation. So in case you want to do like a thermal, electrothermal analysis, so it's possible through this, through EMS 3D. So you can perform magnetic, thermal, and structural analysis within the same study. So you don't need to export or import any data or exchange data between different tools or open another tool to run thermal analysis, for example. So you can have all of these kind of analysis within the same study, within the same model. So you just link your magnetic simulation to thermal, structural, motion, and so on. So you can have all the results folders within the same study. Yeah, so this will help to really reduce any errors in the results through the exporting and or importing of data, increase the productivity of the machine designer. So this is the proposed solution. Now we'll have a look into two case studies. So we'll start by the magnetic gear analysis, then we will see no load analysis of magnetic geared motor, and in the next session, in the part 2 of this webinar, we'll have the loaded analysis of the magnetic gear system. Alright, so we're gonna start now with our first case study, a magnetic gear analysis. So the 3D model of the magnetic gear system is shown. This is the model that will be used or integrated in the permanent magnet synchronous motor later. So it has two or three main structures. It has an outer rotor with 8 poles. It is the low torque high speed rotor, and an inner rotor which is the high torque low speed rotor. It has 18 poles, while the moderator has 13 poles. The gear ratio is 0.44. The 3D model is shown and the 2D model is also shown. So the 2D model was obtained through 2D simplification feature of EMWorks 2D. So EMWorks 2D, which is our 2D electromagnetic simulation software, allows an automated conversion of a 3D to 2D geometry. So you don't need to recreate your 2D model if you want to do 2D analysis, you just simplify or convert your 3D native geometry into 2D geometry. So if you have a 3D geometry, you just use the 2D simplification to get a 2D model ready for simulation. So you don't need to recreate everything from scratch. Right, let's see some results. Magnetic flux results is shown in the left figure. The middle figure or animation contains an animation of the magnetic flux versus position of the inner and outer rotors. So they are rotating at different directions, and H or an animation of H field also shown. So these results are obtained through a parametric study. So the angle of the inner and outer rotors were parameterized, and the results were computed through a parametric study. So within a single study you can have different scenarios or different positions, so you don't need to create different studies. So just a parametric study allows to get different position results. Torque is computed, so both torque results are computed. The inner and the outer torque results is calculated, so it can be seen that the torque, both torque curves has a sinusoidal shape, so they are oscillating around 0, and they have like maximum around maybe 3,500 Newton meter. So this kind of analysis can help to identify the maximum torque position, so you can adjust your rotor's position to get the maximum transmitted torque. Yeah, so the first results or the left figure results were obtained when only one rotor is rotating. The right figure shows the torque results of both rotors when both rotors are rotating at different directions. So you can see the loaded torque. So here it can be seen the steady state torque of our magnetic gear. So also these results were obtained using parametric studies of EMWorks 2D. Right. Now we investigated the torque versus different permanent magnets. So we use a different permanent magnet types, and we are investigating the torque behavior. So it can be seen from the left figure that the air gap flux is increasing with the permanent magnet. So it has different values. So neodymium 55 magnet has the highest resonance. It has resonance around 1.5 Tesla, while the neodymium M42 has a lower resonance, while the grade 8, the ceramic magnet and cobalt magnets have much lower resonance. So it can be observed that their air gap flux, it's the flux across the air gap, across the modulator parts or poles. So it is decreasing with or increasing with the resonance. So with higher with magnets with a higher resonance, we got a higher air gap flux. This will be also more clearer when we see the torque results. So the torque increases with the resonance or the permanent magnet resonance. So it can be seen that the neodymium M55 has the highest torque, so for both inner and outer rotors, while ceramic magnet has the lowest torque because it has the lowest resonance. So this kind of analysis can help to or investigate the use or different permanent magnets. So while the other hand, these magnets, so the neodymium is more expensive and is more it has higher mass density. So there will be some trade-off in choosing the permanent magnet. Now we are computing the losses. So we perform a transient magnetic analysis, so time domain analysis, to compute the losses at different parts of our magnetic gear. Here we can see at the left side that the eddy losses in the magnets were computed. So we can see that total eddy loss in all the magnets is plotted. while in the right figure the iron loss, the core loss versus time also were plotted. So it can be seen different type of losses, eddy, hysteresis and excess loss, and the total core loss results versus time is computed and shown in this graph. Okay, so overall, so 2D analysis is enough and sufficient to get all the needed data and results of such application. So you can run, analyze, optimize your magnetic gear system using 2D analysis. Yeah. Okay, let's now move to our second case study. So now we can see that we replaced the outer rotor with a stator, with windings. So we replaced our magnetic gear outer rotor with another stator. So now we have a 2D model, and we're gonna use a 3D simulation. We're gonna use EMS simulation now. So okay, after running 3D analysis using EMS, whether static analysis or transient analysis, you can obtain the flux density results. So this is a fringe plot of the magnetic flux, while you can see at the right side a vector plot of the magnetic flux. So several options, post-processing options are allowed and available using EMS and EMWorks 2D as well. So you can use a fringe, vector, streamlines, and so on, and maybe 2D plots and so on. So you can visualize your results using any post-processing option. Now we can see here an animation of the magnetic flux versus time. So these analyses were performed using a coupling to motion, to SolidWorks motion. So you can see that the inner rotor is rotating in a direction, and the outer rotor, which is the modulator, which is the ferromagnetic pole pieces, are rotating in the opposite direction. So they have different speed and different torque values. So yeah, so you can apply two different type of motors, two different speeds to the both rotors here. Okay, now we are showing the results of the back EMF versus time. So the back EMF versus time, the back EMF of the inner rotor at speed of 300 RPM is shown at the left figure. So you can see that the back EMF has sinusoidal shape, and it is around 500 volt, while in the right figure we investigated the back EMF results versus speed. So we changed the speed and computed the back EMF at each time. So you can see that the speed increases, or sorry, the back EMF increases when the speed increases. So they are proportional. Another analysis was performed to investigate the short circuit response of this machine. So you can see at the left side the short circuit current versus time. So it has a high current. So as you can see that the short circuit reached values around 80 amp in a very short time. So this is the short circuit response of this machine. The winding loss during this short circuit test is shown at the right side. So the total winding loss are around 2 kilowatts. Okay, now we're gonna see a live demonstration about both EMWorks 2D and EMS inside SolidWorks. Okay, so I switched to SolidWorks. As you can see, this is my 2D model, my magnetic gears, the 2D model of my magnetic gear system. So it is a 2D model. So it was generated through 3D model using 2D simplification of EMWorks 2D. So this is the model that we are gonna simulate. So yeah, as you can see, and as we mentioned, both EMS, EMWorks 2D and Motor Wizard are integrated inside SolidWorks. So they are all inside SolidWorks and Autodesk Inventor. So you can use all of them at the same time within the same platform. So you can do 2D simulation, motor analysis using Motor Wizard, and 3D analysis using EMS. So yeah, let me go to EMS tab here. So now I'm gonna move to EMS tab. Okay, so you can see the studies I solved already. So yeah, this is EMS tab, so you can start by defining a new study. Once this page is open, so you can see 4 modules are available in EMWorks 2D. So magnetostatic for static magnetic analysis, electrostatic for static electric field analysis, AC magnetic for harmonic frequency domain magnetic analysis, and transient magnetic is for time domain magnetic analysis. So you can choose the type of analysis that you want. In addition to this, we can see this parameterization options. So parameterization allows to parameterize both simulation and geometrical variables. So you can parameterize dimensions, distances, angles, and so on using this option. Also, you can parameterize current, voltage, or whatever of the simulation variables. Yeah, let me show now the coupling options available. So you can couple your transient magnetic analysis to thermal, translational motion, rotational motion, and circuit coupling. So you can choose any type of coupling that you want to add, and you can do a combination of this. You can combine motion plus circuit, motion plus thermal, thermal plus circuit, and so on. So you can do this combination multiphysics analysis without the need of changing the software or changing the platform or exporting and importing any data. Okay, let's define simple magnetostatic analysis. So we can choose now what type of symmetry that we have, whether it is planar or axisymmetric. So let's say it is planar. It's the planar, and we have the model length here. Then we create a new study. So once a new study is created, you start by defining the materials. So EMS, EMWorks 2D, and Motor Wizard came with a rich and well organized material library, as can be seen here, for example. So you can see several categories here. We have permanent magnets. Here we have biological materials, cable, ceramics, conductors. We have electrical steers. We have linear, so approximated linear materials. We have several types of materials over here, and you can also customize, edit, and add new materials. So you can define your library, your own library. You can customize the existing materials as well, so whatever you want, so you can do with this material library. Also, you can create automatic pH curves here, so you can like this one. Let me try to create a new library, add a new library here, for example, my library. So yeah, so I added a new library. So okay, new material. Then you can see the properties that you can define. So this is these properties are relative to the study I'm choosing now, which is magnetostatic analysis. So let me show one feature. So you can choose isotropic, orthotropic, or linear. So you can add a curve here, so you can import your pH curve, for example, or PB curve through this library. So you can import through text or an Excel file. So, and you can also create it inside this curve or EMS curves. Then another option, generate points. So you can automatically generate a pH curve when you know the B saturation of your material and the initial permeability. So once you know these two properties, you can automatically generate your pH curve here. So yeah, as you can see, this is a smooth curve. Okay, so you define your materials, you define the boundary conditions. So it's simple. So only one boundary condition is needed. So you apply a magnetic vector potential to the outer edges of your system. or your region. For example, here we should apply a vector potential to these outer edges. Then once you apply your boundary condition, you can specify the type of coil that you have. In case you have coils, you can specify solid or wound coils. So you apply to solid, to surface or edge, so it depends on your needs. Then specify where you wanna compute the force, choose which option, whether it is vertical work, which is used when we have a ferromagnetic material, or Lorentz force for conductive materials. Then mesh and run your analysis, so you'll be able to get the results. So let me show here, so you can find flux results, flux density here, so it can be seen. Just let me create a new plot. So this is a corrupted file. Let me change the study. Yeah, so you can see here we have the flux results, so you can animate those plots. So this option, you can use a probe, you can use listing to view all the nodes, and results are different positions of your model. Also, as mentioned, so we have options like fringe, vector, contour line, field lines, and so on. So, and you can also plot the field between points along edge, along circle, or whatever. So yeah. Okay, results table contains the tabular results, so it contains results like torque, force, resistance, inductance, and so on. Yeah. Okay, so this is let me plot, for example, here the torque versus different angle position, so you can see the torque results of both inner and outer rotors here. Okay, this is overall and briefly about EMWorks 2D. Now I'm gonna switch to EMS. Let me change my SolidWorks session. Sorry, here. This is the permanent magnet synchronous model inside SolidWorks. So this is the 3D model of the magnetic geared permanent magnet synchronous motor. So you can see here the stator with windings. So we have all the windings there. So it has concentrated windings. We have the inner rotor, this one, and the modulator as the outer rotor, which should be connected to our load. Yeah. So perform different analysis to compute the back EMF. So here the magnetostatic study of EMS can be coupled to motion and can help you to get the back EMF results. You don't need to perform transit or time domain analysis using transient magnetic analysis. So here, all the eddy effects are neglected. So since we have ferromagnetic laminated steel, so we just need magnetostatic analysis to compute the back EMF results. So one of the most important feature here, so EMS allows to be coupled to SolidWorks motion. Let me go back here and show the available modules of EMS. So as you can see here, and unlike 2D, we have more modules. We have magnetostatic, AC magnetic, transient magnetic for magnetic analysis, and we have 3 modules for electric field analysis: electrostatic, electric conduction, and EC electric. So we have 6 modules totally in EMS, and we have also the parameterization, which is similar to the 2D. Coupling options, we have thermal. So thermal allows both steady state and transient. We have linear, static, motion, and circuit. So it's these multi-physics options are available in EMS. Yeah, so the motion here allows you to, EMS allows you to couple your magnetic analysis to SolidWorks motion. Let's see a typical study of the motion. So you can see here that it is possible to define 2 rotary motors here. So we're gonna apply 2 different speeds to our machine. So because of the gear ratio, so we'll use higher speed for the inner rotor and the lower speed to the outer rotor. So you can specify two different speeds with different directions as well. So let's animate this. You can see that they are moving in different direction with the different speeds here. Also, you can define torque. So if you want a dynamic analysis, you just define a torque here. For example, apply a torque with a zero value, and the software computes the torque and sends it to SolidWorks motion. SolidWorks motion will convert it into motion, whether it is translational motion or rotational motion. So all the settings available in SolidWorks motion can be coupled with EMS magnetic analysis. So everything that you can define inside SolidWorks motion study can be used or coupled with EMS magnetic analysis. Yeah, same most of the features available in EMWorks 2D, so they are available here. So you can see the same material libraries is available. So yeah, so you can switch between both of them. So you can do 2D analysis here with EMWorks 2D, then go back to EMWorks or EMS 3D, do 3D analysis for validation. Then you wanna go back to 2D. Feasible. You don't need to change the model, you don't need to make your geometrical changes again. So just do the geometrical changes once and that's all. You don't need to each time you change, for example, the 2D model, you don't need to change it again in the 3D model. So one change is enough. So whether you change in the 3D or on the 2D, so yeah, that's all you need. Okay, so this is overall. Let's quickly try to open Motor Wizard. As you can see here, we have a tab of Motor Wizard. This is the 2D, the motor CAD design simulation software. So it allows, to generate a new design motor, or you open a motor from your existing or an existing motor that you have in your system. Otherwise, there is another important feature. This what's called performance calculator. So if you have your own geometry that is not existing among the templates available using Motor Wizard, so you can compute using another tool, whether EMS or EMWorks, EMS 3D or EMWorks 2D, the DQ model, extract the DQ model using some parametric static analysis, then use the DQ inductances here in this performance calculator to generate efficiency map and so on, and all the performance results of your machine without having this machine among the templates that are available inside Motor Wizard. Okay, let me go back. Let's suppose that I wanna build my model from scratch. Let me launch it again here, so you can see Motor Wizard. Launch Motor Wizard. So a new design. So you can see new design here. Yeah, so you choose whether you want to do brushless DC motor or switched reluctance motor. So these two kind of machine are available now. So yeah, so we have the rated parameters, so the machine settings. So we have the rated current, voltage, speed, and so on, the general sizing, number of slots and poles. Then you have in another tab the stator properties. So whether your stator position is outer or inner, then you choose the slot type, square, round and so on. Properties of your stator, so this the core properties, the slot properties, and the material. Then after you defining the stator properties, you go to the rotor properties. You choose the rotor type. So we have several rotor types here: surface mounted with radial magnets. We have spoke, period, and so on types. So yeah, same properties you should define, so relative to your design. Then the materials and the permanent magnet types and so on. Then the windings. So The fourth tab is for the winding, so you can choose whether you do an automatic configuration or a manual configuration of your windings. Okay, so once you define all these settings, so you validate, then you generate your model, and then you go to the simulation stage. So if you generate your geometry here, automatically will be generated geometry. Then you go to the simulation, choose whether you want to do performance calculation, no load cogent torque, no load back EMF, inductance, DQ inductance, on load. So you can do one or more of these analysis. So the performance calculation is a semi-analytical simulation. It's a fast solution that allows you to get an idea about your design without going in depth in FEA analysis, or before going in depth with FEA analysis. Okay, also one more important thing, so if you define something non-consistent, so some parameters can be non-consistent, so the software helps you to identify these issues and solve it. So if you put some values are not consistent with the design, so the software can identify this, help you to fix it as well. You can see here some visualization of the shapes here. So yeah, okay, so that's all for this live demonstration. Now let's go back to our presentation, and we're gonna end with. Alright, so back to the presentation. Now we're gonna move to the QA session. So this is the reference that we use it now. Okay, so this is the QA session part. So in case you have any question, please feel free to type your questions in the chat window. Okay.